today we're going to be taking a 4D STEM dataset and then showing a bunch of different tools that we can use to visualize the actual data. So here what we're doing is we're setting up our 4D STEM experiment. In this case, we want to be running at faster speed, so we're setting our frames per second as 8,000. Then we can set up our virtual images. Here you can kind of get an idea of what this dataset looks like. We can draw a virtual aperture around one of these diffraction spots here, and then we can have an annual detector here. In this case, what we have is we've set the calculation type for that smaller detector to be the centroid amplitude, and then we're calculating the sum using that larger virtual detector. We could set multiple different detectors as well. Here now we've gone into this acquisition tab, and we can start to save all of the data. What we want to do here is save the 4D stack, but once we save this 4D stack, it's very minimal to save any and all of the other virtual detectors as well as the pack bed. And we'll see later that those are very useful when we want to actually look at this data set. At this point, then, we want to make sure that we've got everything saved. We're saving it as an MRC file format, which is a binary file, and then we can set the directory that we're saving into here. We're going to increase the scan size here from 256 to 512 by 512. So this is a fairly modest 4D STEM data set. And once that's all set up, we'll do no point repeats or scan repeats. We can run in this data set. And it should take around 30 seconds for this to complete. This is just a simulated data set. So you can see we've got a amorphous platinum cap, as if this was a fib sample. And then, we can kind of adjust and see the different FFTs of the system. What you'll see here is you'll actually see that at this middle point we have a strained segment. This is kind of like a precipitate here, and we can see the diffraction pattern will go and stretch at this point. Once again, this is a simulated data set, so it's not quite, it's not exactly real, but it's for demonstration purposes. I think this is a good example. So now, once everything is saved, one thing we can do is we can go down to this external analysis, and we can click here on virtual image 1, and then this will open this in ImageJ. So now we can use any of the tools within ImageJ to kind of analyze this virtual image or save it. But this is really only super useful when you're looking at single images like these virtual images, or maybe a movie. If you have something four-dimensional, we're going to have to use a different tool. So now what we're doing is we're opening up the folder in which the dataset is held. You can see here that this is a 34 gigabyte dataset, and if we right click, then we can open up a Jupyter Lab instance. So here what we're doing is we're opening up a Jupyter Lab instance, and these contact actions are given if you install the HyperSpy bundle, which there's a link to in the description. At this time, you've got your Jupyter Notebook, your Jupyter Lab instance opened, and you can see I had some previous calculations that I'd done. So what we're going to want to do is we're going to want to import HyperSpy, and we can use this HyperSpy.load function. And here, if we press Tab, then we can get all of the files within this folder. So here we're going to want to load this movie, the MRC, and we can, in this metadata file parameter, then we can set the .info.text file that's saved alongside. And what this will do is that this will automatically load things like the camera length, the magnification, but also the shape of the data set that we've saved. An important parameter here is also this lazy is equal to true. Basically what lazy is equal to true means is that it means that the data is not actually loaded into memory. And so instead, if you actually if you just push Shift Enter after you type dataset 4D, you'll get this nice representation, which this shows the different chunks. This shows how the dataset is loaded, and so each of these chunks is a separate part of the dataset that's loaded into RAM, and then once you move on to the next part of the dataset, that part will be kind of thrown away. But what's important is that our chunks are set up nicely. So here what I'm doing is I'm setting our chunks is equal to 32 by 32, and then that -1 means that it just spans that axis. And so now you can see when you look at the signal axes, there'll be a flat. And basically what this is saying is that for every diffraction pattern, it's going to be only in one chunk. Now what we can do is we can go and look at the virtual images. And so if we load our individual virtual images here, what you can see is that those can just be loaded just directly into memory. And so we don't have that lazy is equal to true. We don't have to pass anything like the metadata. These automatically will know that these are going to be two-dimensional images. And once these are loaded, we can press Shift Enter, and that will run those cells and load them. And then what we can do is we can plot. So we can just take this center image.plot, and we'll see much the same thing we saw with image J. Now if we want to make this interactive, we can use what's called Jupyter Magic. So here we'll use the matplotlib, ipymatplotlib, ipympl, and then now this is interactive. You can see if I can resize the shape of that image. If I put my cursor over it, you can see the individual values and stuff being shown below. But now if we want to actually load and show the four-dimensional data set, one thing that we can do is that we can set this .navigator attribute. And what this will do is this will pass along this navigator, and it will use that as we plot the whole four-dimensional data set, and this will make things happen quite a bit faster when we call this plot function. So you can see it happens immediately, even though everything is not loaded into your system's RAM and memory. So here, the easiest way to kind of navigate these data sets is to hold down Shift and then to left click, and then it will jump to the position of your cursor on that data set here. So here we can kind of see that as we move around, we can jump to the region which is strained. We can go up to this fake platinum cap, which is amorphous, and then above that there's some vacuum right there. We can also take this navigator keyword and then set our navigator is equal to our centroid image. And what that will do is that will replace that sum image with the centroid image, and now we can more directly see, and we can use that as kind of how we navigate around in real space. And this is really important, especially if you want to try and figure out why something in that virtual image kind of looks the way it does. Hopefully this helps. Please let us know in the comments if there are any additional videos that you'd like us to make or any content that you are interested. And thanks for watching.